In this lesson, we're going to take a look at dividing and multiplying measured numbers. Now, basically what we're trying to do is figure out the correct way to round. And that's because when we do some multiplication or division on a calculator, like if we took 3.7 and divided it by 2.3, we would get a number that has a whole bunch of decimal points afterwards. And we can't report all of those. And the reason we can't report those is because they're telling us that our calculated measurement is more accurate than our measured numbers, and that's not the case. So we're going to look at the rule on how we round stuff today. Now, first thing we have to understand is that all measurements have some uncertainty. Remember, that's because when you have a scale, like a ruler, and you've got divisions on it, and if we're measuring something and the boundary falls right here, we don't know exactly where that is. So if this is 4 and this is 5, then we would say that that boundary is at 4.5 centimeters, and that's an estimate. We don't know exactly for sure what it is, but it does tell us something about the accuracy of this measurement. We know it's accurate to here, and anything beyond that is too much of a guess for us to know. And so this number right here would have 2 significant digits in it. Now, if this scale was divided up into tenths, and then we could measure even more and we could say 4.47, this number would have 3 significant digits in it because it's got 3 non-zero values in it that tell me about the accuracy of the number. So like I said, when calculators do the math for us, they report too many significant digits and we have to round that. And so basically the rule on that is whatever our least number of significant digits is, that's how many significant digits we should put in our final answer. So whatever our least number of significant digits is, that's the one that we're going to use when we finally round our answer. So 9.82 grams has 3 significant digits in it. 1, 2, 3. 3.2 cubic centimeters has 2 significant digits in it. 2, which means our final answer can only have 2 because it's got the least amount. 2 significant digits. So 3 significance there, 2 significance in our other measurement, which means our final answer should only have 2 significant digits. And when we do the math, our calculator says 3.06875. Now, that's got 1, 2, 3, 4, 5, 6 significant digits. And it's telling us it's precise all the way out to this many decimal points. But we can only be precise with 2 significant digits. The 3 stays, that's our first significant digit. What do we do with the rest of this stuff? Well, we round, we need one more number. So 3 point what? Well, 3.06. We don't need the 6, so we look back here and we round that up since our 6 is bigger. So that's 3.1, and this is grams per cubic centimeter. So we would report this measurement as 3.1 grams per cubic centimeter because that has our 2 significant digits. Now, how do we know if a digit is significant or not? Well, all non-zero numbers are significant. So what I mean by that, if I had a measurement that was 4.372 centimeters, that would be 4 significant digits because it's got 4 digits in it, none of them are zeros. However, if I had 4.072, these would still all be significant because this 0 is telling me the value of that place. It's telling me about the accuracy of my measurement. 12.30 also has 4 significant digits. So zeros that tell us about accuracy are significant. Because 12.3, we are saying this number right here is our estimate. But 12.30, we're saying we know this number and this number is our estimate. So that 0 does tell me something about the accuracy of our number. However, 0.23, that 0 out front doesn't tell us anything. It's just like, oh, the decimal point is right here. Same with this. This point 0.06, these two zeros are just putting my decimal point in, and so only that 6 is significant. So zeros are sometimes a little tricky, but essentially if the 0 tells us more information, it's significant. If it just locates a decimal point, it's not.